Hey everyone, I'm here with another one. We're going to talk about some implicit differentiation examples, and this is just for people that just need to see like just more problems worked out, want to see the implicit differentiation like being done, a little bit more of a breakdown. There's no pressure of finishing on time in class or whatever. So yeah, definitely watch this at your leisure. But yeah, and recommend it to others too, just in case if you know someone that is also struggling with this stuff. So let's get to it. So this problem, it is in section 3.7. We're talking about implicit differentiation, and it's kind of like a combination problem, right? So we're going to have to use implicit differentiation because we want to find the tangent and the normal. Okay, the tangent and the normal. So I'm going to cheat a little. I'm going to show you guys, or I'm just going to tell you guys that this is an ellipse. Well, I mean, it tells you that it's an ellipse, and it kind of looks like that. All right, I know it's very potato looking, but yeah, it's the point. The point is kind of like up there, like -1, 2. So just to give you like kind of like a pictorial like reference, right? What we're trying to do here is we are trying to find the equation of the tangent line and the equation of the normal line. Why? I don't know. But this does actually this actually does have you know practical uses, right? A lot of things travel in ellipses, like orbiting planets and things like that. So let's say we want to find the travel path of a planet or something, and we want to find the rate of change that it is changing at that point. All right, so that's for the tangent line. I don't know about the normal line. You can think of something, but here we go. We want to find the tangent line. So just like before, we need the derivative function, right? And since we have an implicitly defined function here, we're going to have to derive it implicitly. So here we go. I'm going to derive this whole entire equation, right? Just like we learned in class. The x's you just leave alone, or I'm sorry, the x's you just treat them like normal, right? So this first term just becomes 2x. The second term, all right, which is -xy, I have a product of two functions here. So I'm going to need the product rule, right? So what I'm going to do is actually I'm going to highlight this negative because a lot of people tend to forget it. And then we do the product rule on the inside. So it's first times the derivative of y, which is just y prime, right? Which is dy. This is also dy dx. It's the same thing, right? So, but I'm just going to write y prime because it's faster. So first times the derivative of the second plus second, which is y, times the derivative of the first, which is just 1. Okay, I left the negative out, so it's actually not -1. If I didn't leave the negative out, then I would have to consider the negative. Does that make sense? Like, there's a difference between plus like this whole function versus minus like the two functions being multiplied together. I decided to split it up, but either way, you get -xy. I'm sorry, -xy prime minus y after you distribute that through, okay? And then we can't forget the rest of the equation. So this becomes plus 2y, and just like we learned in class, just because y is technically like deriving y is like deriving a composed function, right? A y prime is going to poop out, right? So we're left with plus 2y y prime equals 0 because the derivative of 7 is 0. All right? So from here, we collect all of our y prime terms, and then we just push everything else to the other side. So that means this goes to the other side, and this goes to the other side, because the other two terms are going to have a y prime in which we can factor out, right? So I'm actually going to do this all in one step. So I'm going to move the yellow pieces over, and then factor out the y prime on the left side, and I'm going to be left with y prime times let me switch the order here. 2y minus x. Okay, because the 2y and the minus x were left over. And then on the other side, it's going to be -2x up. Let me just keep this consistent here. Y minus 2x. Because I added the y and then I subtracted 2x. Duh. All right. And look, there's our dy dx. It's almost alone. All we need to do is divide both sides by 2y minus x. I was going to say derive. 2y minus x, 2y minus x. I get it. It's not a pretty function, but hey, it's an implicitly defined function, right? Like, what do you expect? Y minus 2x all over 2y minus x. And that is the slope function. That is my derivative function. I'm going to use that term loosely here, but that is my derivative equation for the tangent line for the ellipse. And since our interested point, our point we're in the point we're interested in is negative 1, 2. We're going to plug that into y prime, right? So we're going to plug. So here's the notation: dy dx evaluated at negative 1, 2. All right, so that means I'm going to plug in negative, let me just double check. Yeah, negative 1, 2. So I'm going to plug in negative 1 for x, 2 for y, so it becomes 2 plus 2 over 4 plus 1. And there it is. That's my slope of the tangent line. So that's 4/5. All I need to do is now put that into the point slope formula, and the tangent line goes y minus y1 is equal to the slope, x plus 1. And there it is. That's my tangent line. Right, and then the normal line is just going to be, if you remember, it's the same exact thing. It's just the negative reciprocal, right? So it goes y minus 2 is equal to negative 5/4 of x plus 1. And there it is. That's your tangent line and normal line. All right, let's do another one. All right, so I figure the second example should deal with, inverse trig function, since, we kind of talked about that today briefly. So let me look at this one. I got y equals sine inverse of x over 4. And then it's asking for the tangent line at x equals 3. Okay, so tangent line at x equals 3. So here we go. I'm going to need to derive this thing, plug in 3, and yada yada yada. I also see that this has to be a calculator question. Has to, because if I'm going to plug 3 into an inverse function, I'm going to get some weird, they didn't give us something with a pi in it. So this one is definitely a calculator question. So as always, 3 decimal places, don't forget. All right, so here we go. Let me first find y prime, because we learned how to do that today, right? So the derivative of sine inverse of just x, if it was just sine inverse of just x, right? We learned this today. This is going to be 1 over root 1 minus x squared. All right, and then cosine is the negative version of that. But yeah, this is sine. But in this case, I don't have an x. I actually have an x over 4. Right? So there's a couple ways you can go about this. I'm going to do it a slightly longer way, just so that it's a lot more explicit. I'm going to turn x over 4 into a u, because technically this is a chain rule function. I'm sorry, this is a chain rule problem, right? So what I'm going to do is I'm going to call this sine inverse of u, where u is x over 4. And we know du dx is just 1/4. Right? And we're going to need that, right? So the derivative is going to be dy du times du dx, right? Since there's just one chain, or I guess 2 chains. I always screw that up. But anyways, yeah, so the outer function we're going to derive as normal, right? It's going to be 1 over root 1 minus u squared. And then times the derivative of du dx, which we just said was 1/4. So why don't we put that down there? Okay, but remember, we want to keep everything, in the same variable. We want to make sure that our answer is in terms of x. So I'm just going to swap this out. This becomes 1 over 4 root 1 minus x over 4, x squared over 16. I'll call it that for now. Okay. A lot of the times you'll see in books get a different answer, okay? But just know that this is the answer. This is the answer for the derivative of y. But a lot of books, what they're going to do is, I kind of call this force factoring. It's when you factor out numbers that actually aren't divisible by there is no common factor for you to pull out, right? Like you're used to seeing problems like 2b or not. 2b plus 2a, you would factor out the 2 only because they have a common thing of 2, right? But what you may not know is that you can factor out anything you want, right? Sky's the limit. In this case, if I have 1 minus x squared over 16, I can make this look quote unquote prettier by factoring out a 1 over 16, right? And this is actually going to be a trick that we use later on too. So what does this become? That means I need something times 1/16 to get me 1. Well, the only number that works with is 16. And then what am I going to be left with here? An x squared. So you see that? You see how I like force factored out a 1/16? Right? And if that's the case, that means that this is all still under the root, right? Because it's still under that root there. So what's really going to happen to this 1/16? It's going to pop out as a 1/4, and oh my gosh, there's a 4 out there. So that 4 and the 1/4 that pops out are actually going to cancel out. So a lot of times you'll see this trick. The books usually like to rewrite it as 1 over root 16 minus x squared. It looks prettier. It doesn't have a fraction within a fraction and under the square root and so. But yeah, so you might have to do that on your homeworks or whatever. All right. So what did we just do? We just derived it. Now we need to tangent line. Right. Okay. So I have my derivative function. It's right here. I'm going to plug in 3. So I'm going to go dy dx evaluated at x equals 3. And I got 0.37. I'm just going to go 8, but I'm going to save this value in my calculator. It's like 0.337, no, it's 0.377964473, yada, yada, yada. All right, so I'm going to save that value in my calculator, but on paper, I'm just going to round it to 0.378. There's my slope. I go y minus, so I got to see what pops out when I plug in 3 into my function now. So my y of 3 is equal to sine inverse of 3 over 4. I'm just going to punch that into the calculator real quick. Sine inverse of 3/4, which is 0.84806 something. So putting it all together, it's y minus 0.848 equals the slope, which is 0.378 x minus 3. And I am definitely not going to simplify that. I'm good. If you want to simplify it, you can. All right, so here are 2 examples. One dealing with inverse trig. The other one just talking about implicit functions. Implicitly deriving functions. As always, reach out if you have any questions, and have a nice day.